Now we're on number 29, integral from 1 to infinity, ln x over 1 over x squared dx. Why is this improper? Well, this limit's infinite. We have a domain restriction. We do not. The denominators will always be not the zero because something squared will always be, well, at the bare minimum, be zero, and then we're adding 1. So we're okay there. Okay, so how do we do this? You might be able to directly evaluate it, actually. I decided to do a comparison test like this. This might not be the easiest way. I'll say that right away. But this is how I thought through it. And it's a solution, possible solution, okay? So if you got totally stuck, maybe you can try to see how I thought through it, and then you can try a similar function to compare with, or something like that, all right? As a studying technique. So this function, ln x over 1 plus x squared, I know that it's less than or equal to ln x over x squared for x is greater than or equal to 1, okay? How do I know that, by the way? Well, the denominator is bigger here by adding an additional 1. So that means we're going to be dividing by more, which means the final value is smaller. Okay? This integral over here, or I guess right here, I can evaluate by integration by parts. Okay? And the reason I want to evaluate this and not this one, at least for me, is because if I choose my u to be ln x, dv is, for this guy, it'll be 1 over 1 plus x squared. That becomes arctangent when I integrate. So I didn't want to do that. So I chose a simpler function to integrate instead. This one is much nicer, at least from the beginning. It looks nicer. So I proceeded with this, okay? Integration by parts, you would get minus ln x over x minus 1 over x plus c. So this is the indefinite integral. So let's do the improper integral now. From 1 to infinity, ln x over x squared dx, same function. We're going to use this antiderivative to the fundamental theorem of calculus, and with the proper limit notation, I wrote it in, okay? If we evaluate the limit, it is 1. It looks like I used L'Hopital's, so you can check that out yourself. So since this converges, this improper integral, and our guy is even smaller, then our guy is going to converge as well. I don't think I ever said this actually, but recall that integral is area under the curve. So if this guy is finite, it's a finite area, okay? You know, it's really infinite, but let's say it's, for illustration purpose, let's say it's finite, okay? It's finite, okay? Something smaller, the area under this guy will be even smaller. So for sure, it's going to be finite as well. So that's how the comparison test works. Since this guy converged, it's finite. Something smaller, something with less area will for sure converge as well.